Hello friends, welcome you all to the 40th lecture on function analysis and its applications. In this lecture, we will discuss the Gram-Schmidt orthogonalization process. This is the content of today's lecture, Gram-Schmidt orthogonalization process. Okay, theorem of Gram-Schmidt orthogonalization process. This is also known as Gram-Schmidt orthonormalization process. Theorem. Let S is equal to U1, U2 and so on Un be linearly independent set or basis in a Hilbert space H. Then there exists an orthonormal set of vectors S1 is equal to W1, W2 and so on Wn, such that linear span of S is equal to linear span of S1. Proof. Let S is equal to U1, U2 and so on Un be linearly independent set or basis in Hilbert space H to construct an orthonormal set S1 equal to W1, W2 and so on Wn, such that linear span of S equal to linear span of S1. Now we shall construct an orthonormal set S1, that is set of W1, W2 and so on Wn in H by the help of the element of S. The main idea behind this construction is that each Wi is linear combination of vectors belonging to S. Since S is basis, this implies that S is linearly independent. This implies that Ui non-zero vector for all I lies between 1 to n. Set V1 is equal to U1 and V2 is equal to U2 minus inner product of U2 V1 upon norm of V1 square into V1. Okay. And V1 is equal to U1, that is V2 is equal to U2 minus inner product of U2 U1 upon norm of V1 square into U1. Okay, because V1 is equal to U1. For V2 is equal to 0, this implies that U2 is a scalar multiple of U1. Okay, if V2 is equal to 0, then U2 is equal to this one. Okay, for this construction, this is a linearly dependent. For V2 is equal to 0, this implies that the set U2 and Un is linearly dependent, which is a contradiction as U2 Un is linearly independent. Consequently, V2 not equal to 0. Then inner product of V2 V1 equal to inner product of this and V1, putting the value of V2 from here. Put the value of V1 is equal to U1, so we have this one, and applying the property of inner product, that is inner product of U2 U1 minus inner product of this into U1 and U1. Okay, so inner product of U2 U1 upon norm of V1 square, that is scalar, so we can write the outside the inner product of this. So this can be written as inner product of U2 U1 and minus inner product of U2 U1 upon norm of V1 square into inner product of U1 U1. Okay. So U1 is V1. So this can be written as norm of V1 square. So this is and this one cancelled out. Therefore, inner product of U2 U1 minus inner product of U2 U1 is equal to 0. Hence, V2 is orthogonal to V1, and therefore set V1 V2 is an orthogonal set. Set V3 is equal to this, U3 minus summation I is equal to 1 to 2 inner product of U3 Vi upon norm of Vi square into Vi. Expanding this, so this is U3, and if I is equal to 1, that is inner product of U3 V1 upon norm of V1 square into V1 minus, putting I is equal to 2, so minus inner product of U3 V2 upon norm V2 square into V2. Okay. Again putting the value of V1 and V2 from above, this and this, we can write U3 minus inner product of U3 U1 upon norm of V1 square into U1 minus 1 upon norm V2 square, and inner product this into this U3 and putting the value of V2 here, this into V2, this one. Okay, by putting the values of V1 and V2. So solving this, we get this one. Okay, here this and this as it is, and this is 1 upon norm V2 square, and this is inner product of this U3 and U2 plus this. Okay, so this is inner product of U3 U2 and inner product of U3 and this part with negative sign. So after simplifying, this part can be written as this. Okay, 1 upon norm V2 square and inner product of U3 U2, and outside the inner product this is U2 U1 bar into U3 U1 upon norm V2 square into norm V1 square. Okay, into this one. Now multiplying this with this, we have U3 and this part, and this is also minus U3 U2 upon norm of V2 square into U2. Okay, multiplying this one, and this multiplying this, we have this one, and again this multiplying with this and this with this, we have this one. Okay, so this is simple calculation. So at last we simplifying this with the coefficient of U3, U2 and U1. We have this U3 plus some coefficient of U2 and some coefficient of Un. Okay, so for V3 is equal to 0. So U3 is linear combination of the vector U2 and U1. So for V3 is equal to 0, this implies that U1, U2, U3 is linearly dependent, which is a contradiction as U1, U2, U3 is linearly independent. Now if V3 not equal to 0, we have inner product of V3 V1. So putting the value of V3, that is U3 minus inner product of U3 V1 upon norm of V1 square into V1 minus inner product of U3 and V2 upon norm V2 square into V2 and V1. Okay, simplifying this using the property of inner product. So this is inner product of U3 V1 minus inner product of U3 V1 into inner product of V1 V1 upon norm of V1 square minus inner product of U3 V2 upon norm V2 square into inner product of V2 V1. Okay, this equal to inner product of U3 V1 minus inner product of U3 V1, this is norm of V1 square upon norm of V1 square, and V2 V1 is orthogonal vectors, that is inner product of V1 V2 is equal to 0. So we have this and this norm of V1 square upon norm of V1 square cancel out. So we have inner product of U3 V1 minus inner product of U3 V1, that is 0. So V3 is orthogonal to V1. Similarly, inner product of V3 V2. Putting the value of V3 here, this as above, and V2. So inner product of U3 V2 minus scalar inner product of U3 V1 upon norm of V1 square into inner product of V1 V2 minus scalar inner product of U3 V2 upon norm of V2 square into inner product of V2 V2. Okay, again V1 orthogonal to V2, that is this portion is 0, and inner product of V2 V2 is equal to norm of V2 square upon norm of V2 square. Okay, so this is cancelled out. So we have inner product of U3 V2 minus inner product of U3 V2, that is 0. Thus proceeding in this way, we have inner product of Vi Vj is equal to 0 if I not equal to j, for all ij is equal to 1, 2, 3 and so on. Further, we constructed an orthogonal set V1, V2 and so on Vk of k vectors such that Vk is equal to Uk minus summation I is equal to 1 to k minus 1 inner product of Uk Vi upon norm of Vi square into Vi. If Vk plus 1 is equal to 0, this implies that U1, U2 and so on Uk plus 1 is linearly dependent, which is a contradiction as U1, U2 and so on Uk plus 1 is linearly independent. Okay. If 1 less or equal to j less or equal to k, then for Vk plus 1 not equal to 0, we have inner product of Vk plus 1 Vj. Putting value of Vk plus 1, okay, from here by replacing k is equal to k plus 1. Okay, so this is inner product of u k plus 1 minus summation I is equal to 1 to k inner product of u k plus 1 vi upon norm of vi square into vi and vj. So simplifying this, so inner product of uk plus 1 vj minus inner product of this vector and vj. Again, this is as scalar and simplifying in summation, so we can write this as minus summation 1 is equal to k and scalar this into inner product of vi vj. Okay. So if we simplifying this, I is equal to 1 to k, so here if I and j equal, then value of this is 1, otherwise 0. So only one term we have, inner product of uk plus 1 vj upon norm vj square into inner product of vj vj. that is this one, equal to inner product of uk plus 1 vj minus inner product of uk plus 1 vj, and this is norm of vj square upon norm of vj square. So this is cancelled out. So we have inner product of uk plus 1 vj minus inner product of uk plus 1 vj, that is 0. Consequently, inner product of vi vj is equal to 0 for I not equal to j, and ij lies between 1 to k plus 1. So our M is now completed by induction. Thus we have constructed an orthogonal set V1, V2 and so on Vn of n vectors. Now putting Wi is equal to Vi upon norm of Vi. So norm of Wi equal to norm of Vi upon norm of Vi, that is 1. So this implies that norm of Wi is equal to 1. Then set W1, W2 and so on Wn is an orthonormal set in which every vector is unit vector, meaning thereby S1 equal to set W1, W2 and so on Wn is an orthonormal set of n vectors in H. Since an orthonormal set is linearly independent, it has been proved already in theorem 5 of lecture 37. Okay. So orthonormal set is linearly independent, hence S1 is linearly independent. Hence S1 equal to set W1, W2 and so on Wn is an orthonormal set of vectors in H. By the above expression, linear span of U1, U2 and so on Un is equal to linear span of the W1, W2 and so on Wn. That is, linear span of S is equal to linear span of S1. Okay. This completes the proof of theorem. Noting point, since Wi is equal to V upon norm of Vi, suppose I is equal to 1, then W1 equal to V1 upon norm of V1. This implies that V1 is equal to W1 into norm of V1. Equation 1. For I is equal to 2, W2 is equal to V2 upon norm of V2. Okay. Since V2 is equal to U2 minus inner product of U2 V1 into V1 upon norm of V1. Okay. Equal to U2 minus, putting the value of V1 from equation 1 in this equation, we have U2 minus inner product of U2 W1 norm V1 into W1 norm V1 upon norm of V1. Norm of V1 is real scalar, so we can write outside the inner product. So U2 minus inner product of U2 and W1 into norm of V1 square upon norm of V1 square. That is norm of V1 square and norm of V1 square, that is cancelled out. So V2 is equal to U2 minus inner product of U2 W1 into W1. So V2 can be written as in terms of W1 as this. Therefore, from equation 2 and 4, we have V2 is this, omega 2 is equal to V2 upon norm of V2, that is V2 is equal to this upon norm of this. And taking norm of W2, that is norm of this upon norm of this, that is 1. Now check the orthogonality. Then inner product of W2 and W1 is putting the value of norm of W2 in this inner product, here W1. So simplifying this, so this is scalar, so we can write this is outside the inner product, and simplifying this equal to inner product of U2 W1 minus inner product of U2 W1 into inner product of W1 and W1 upon norm of this. Inner product of W1 and W1, that is norm of W1 square. Okay, that is 1 from, yes. So we have inner product of U2 W1 minus inner product of U2 W1 upon this. So this is cancelled out. That is 0 upon this, that is 0. So omega 2 orthogonal to omega 1. Similarly, we can prove W3 is equal to this one. Okay, and inner product of W3 and W2 is 0, W3 and W1 is equal to 0, norm of W3 is equal to 1, and so on. So we can represent the V1, V2, V3 in terms of W1, W2, W3 also here, and W1, W2, W3 can be written as in terms of U1, U2, U3 and W1, W2, W3. Numerical problems on orthogonalization. Let S be a subspace of a Hilbert space H spanned by the vectors 0, 1, 1, 0, 0, 5, minus 3, minus 2, minus 3, minus 3, 5, minus 7. Find an orthonormal basis for S. Solution. Given set, this is linearly independent. Consider U1 is equal to first vector, this, and U2 is equal to second vector, U3 is equal to third vector. Okay. So applying Gram-Schmidt orthonormalization process, let V1 is equal to U1, tuples of 0, 1, 1, 0. Then norm of V1 square is equal to summation I is equal to 1 to n mod V1 I square, that is 0 square plus 1 square plus 1 square plus 0 square, that is 2. Let V2 is equal to U2 minus inner product of U2 V1 upon norm of V1 square into V1. So putting the value of V1 is equal to U1 equal to U2 minus inner product of U2 U1 upon norm of U1 square into U1. This equal to putting the value of vector U2, this, and inner product of U2 and U1 upon norm of U1 square into U1. So this is the inner product. So this into this plus 5 into 1 plus minus 3 into 1 plus minus 2 into 0. This is upon 2 into 0, 1, 1, 0. Okay. So this vector as it is minus, simplifying this is 0 plus 5 minus 3 minus 0 upon 2, this is the vector this. So this is 5 minus 3, that is 2, 2 upon 2 into vector this, and this is as it is. And this is equal to this minus this one. So 0 minus 0, that is 0, 5 minus 1, that is 4, minus 3 minus 1 minus 4, minus 2 minus 0, that is minus 2. Okay. So vector V2 is this one. Okay. So norm of V2 square equal to square of the 0 plus square of the 4 plus square of the minus 4 plus square of the minus 2, that is 36. Similarly, let V3 is equal to this, as above discussed in Gram-Schmidt orthogonalization process. Okay, V3 is equal to U3 minus inner product of U3 V1 upon norm of V1 square into V1 minus inner product of U3 V2 upon norm of V2 square into V2. So as above, we solve it, okay, by putting the value of U3 here and inner product of U3 and V1 already given. V1 is equal to U1 and here inner product of U3 V2. So just we obtain the value of V2, this, so putting here and simplifying as like this. Okay, in similar pattern as the explanation of V2. Okay, so after simplification we have V3 is equal to vector tuples of minus 3, minus 2, 2 and minus 8. Okay, this is the vector V3. Then norm V3 square is equal to square of the minus 3 plus square of the minus 2 plus square of the 2 plus square of the minus 8, that is 81. Consequently, the required orthonormal basis for S is S1 is equal to set of the V1 upon norm of V1, V2 upon norm of V2, V3 upon norm of V3. That is, this is W1, W2, W3. That is this one. In this lecture, we have discussed the Gram-Schmidt orthogonalization process with an example. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narsey. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterrudin. Thank you.